Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 6, Algebra of Points and One-Dimensional Coordinate Systems. Section 58, Homogeneous Coordinates on a Line. The exceptional character of the point P infinity, as the coordinate of which we introduced a symbol infinity with exceptional properties, often proves troublesome, and is, moreover, contrary to the spirit of projective geometry, in which the points of a line are all equivalent. Indeed, the choice of the point P infinity was entirely arbitrary. It is exceptional only in its relation to the operation of addition, multiplication, etc., which we have defined in terms of it. In this section, we will describe another method of denoting points on a line by numbers, whereby it is not necessary to use any exceptional symbol. As before, let a scale be established on a line by choosing any 3 points to be the points P0, P1, P infinity, and let each point of the line be denoted by its non-homogeneous coordinates in a number system isomorphic with the points of the line. We will now associate with every point a pair of numbers x1, x2 of this system in a given order, such that if x is the non-homogeneous coordinate of any point distinct from P infinity, the pair x1, x2 associated with the point x satisfies the relation x equal to x1 divided by x2. With the point P infinity, we associate any pair of the form k0, where k is any number, k not equal to 0, of the number system isomorphic with the line. To every point of the line corresponds a pair of numbers, and to every pair of numbers in the field, except the pair 0, 0, corresponds to a unique point of the line. These two numbers are called homogeneous coordinates of the point with which they are associated. The pair of numbers is said to represent the point. This representation of points on a line by pairs of numbers is not unique, since only the ratio of the two coordinates is determined, i.e., the pairs x1, x2 and mx1, mx2 represents the same point for all values of m different from 0. The point P0 is characterized by the fact that x1 is equal to 0. The point P infinity by the fact that x2 is equal to 0, and the point P1 by the fact that x1 is equal to x2. Theorem 15. In homogeneous coordinates, a projectivity on a line is represented by a linear homogeneous transformation in two variables. Equations 1. Rho x1 prime is equal to ax1 plus bx2. Rho x2 prime is equal to cx1 plus dx2, where AD minus BC is not equal to 0, where rho is an arbitrary factor of proportionality. Assumptions A, E, and P. Proof. By division, this clearly leads to the transformation, equation 2. X prime is equal to ax plus b divided by cx plus d, provided x2 prime and x2 are both different from 0. If x2 is equal to 0, the transformation, equation 1, gives the point x1 prime, x2 prime equal to a, c, i.e., the point P infinity equal to 1, 0 is transformed by equation 1 into the point whose non-homogeneous coordinate is a divided by c. And if x2 prime is equal to 0, we have in equation 1 x1, x2 is equal to d, minus c, i.e., equation 1 transforms the point whose non-homogeneous coordinate is minus d divided by c into the point P infinity. By reference to Theorem 11, the validity of this theorem is therefore established. As before, the matrix A, B, C, D of the coefficients may conveniently be used to represent the projectivity. The double points of the projectivity, if existent, are obtained in homogeneous coordinates as follows. The coordinates of a double point x1, x2 must satisfy the equations rho x1 equal to ax1 plus bx2 and rho x2 equal to cx1 plus dx2. These equations are compatible only if the determinant of the system vanishes. Equation 3, the quantity a minus rho times x1 plus b times x2 is equal to 0, and cx1 plus the quantity d minus rho times x2 is equal to 0. This leads to the equations the determinant of a minus rho, b, c, d minus rho equal to 0. For the determination of the factor of proportionality, rho, this equation is called the characteristic equation of the matrix representing the projectivity. Every value of rho satisfying this equation then leads to a double point when substituted into one of the equations 3. Namely, if rho 1 be a solution to the characteristic equation, the point x1, x2 is equal to minus b, comma, a minus rho 1 equal to d minus rho 1, comma, minus c is a double point. Footnote, this point is indeterminate only if b is equal to c is equal to 0 and a is equal to d. The projectivity is then the identity. In homogeneous coordinates, the cross ratio R of AB, CD of 4 points, A equal to A1, A2, B equal to B1, B2, C equal to C1, C2, D equal to D1, D2, is given by R of AB, CD is equal to AC divided by AD divided by BC divided by BD, where the expressions AC, etc., are used as abbreviations for A1C2 minus A2C1, etc. This statement is readily verified by writing down the above ratio in terms of the non-homogeneous coordinates of the 4 points. We will close this section by giving to the two homogeneous coordinates of a point on a line an explicit geometrical significance, in view of the fact that the coordinates of such a point are not uniquely determined. A factor of proportionality being entirely arbitrary, there may be many such interpretations. On account of the existence of this arbitrary factor, we may oppose a further condition on the coordinates x1, x2 of a point. In addition to the defining relation x1 divided by x2 is equal to x, where x is the non-homogeneous coordinates of the point in question, we choose the relation x1 plus x2 equal to 1. If this relation is satisfied, a1 is equal to the determinant 1 minus 1, 1, 0, divided by the determinant 1 minus 1, x1, x2, divided by the determinant 0, 1, 1, 0, divided by the determinant 0, 1, x1, x2, is equal to the cross ratio R of minus 1, 0, comma, infinity x. x2 is equal to determinant 1 minus 1, 0, 1, divided by the determinant 1 minus 1, x1, x2, divided by the determinant 1, 0, 0, 1, divided by the determinant 1, 0, x1, x2, is equal to the cross ratio minus 1 infinity, comma, 0, x. Thus, homogeneous coordinates subject to the condition x1 plus x2 equal to 1 can be defined by choosing 3 points A, B, C arbitrarily and letting x1 equal to the cross ratio R of AB, CX and x2 equal to the cross ratio R of AC, BX. The ordinary homogeneous coordinates would then be defined as any two numbers proportional to these two cross ratios. Footnote: the point minus 1, 1 forms an exception in the definition of homogeneous coordinates subject to the condition x1 plus x2 is equal to 1. An exceptional point or points will always exist if homogeneous coordinates are subjected to a non-homogeneous condition.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.